This is level 1 of the CFA program, the topic on quantitative methods, and the reading on hypothesis testing. It's my understanding that this series of readings is quite challenging for candidates, but especially this reading on hypothesis testing. So my role here is to try to simplify this for you so that you can, kind of wrap your arms around what we're doing. And to accomplish that, let me just tell you a quick little story about my son. When my son was about 5 or 6 years old, he fell in love with monster trucks. And so I took him to a monster truck show. And, sometime during the monster truck show, he looked up at me and said, "Hey, Daddy, a Gravedigger is by far the best monster truck. I love Gravedigger." And so as a good academic, I looked down at my son with love and I said, "Well, son, let's go ahead and let's test your hypothesis. Let's get out a tape measure and let's measure the height of all of the monster trucks as they fly over. And how about the length? How high do they go and how far do they go? And let's get an audio recording device and let's measure the volume of the sound because these machines are so powerful. Let's collect all of this data and let's test your hypothesis with some terrific econometrics testing." And of course, my son looked up at me and said, Daddy, I don't need to do all that stuff that you do at school. I know Gravedigger is the best out there. Now, of course, we just can't take my son's attitude because he loved Gravedigger, but as good financial analysts, we're going to be faced with the question that sounds something like this. Which firms have an optimal capital structure? Which firms pay the right dividend? When we're trying to find undervalued securities, maybe we want to know about operating cash flows and free cash flows, maybe price earnings ratios. If we're fixed income analysts, of course we want to know about duration and convexity and default risk and the price of credit default swaps. So we have to collect all of this data and we have an idea. We have an idea that sounds something like this kind of a firm ought to pay a 5% dividend yield. Or this kind of a bond ought to have a credit default swap price of 75 basis points. So we have this idea and we need to test it. We need to decide whether or not we're right or we're wrong. We need to prove it. And that's all we're doing in hypothesis testing. And so in order to complicate life for you, let's go ahead and look at some of these learning outcome statements. All right, that first one should be okay. Steps in hypothesis testing. 1 and 2-tailed tests, type 1 and type 2 errors. This is going to be important. And we'll go through this relatively slowly at the first part of the slide deck. But then we need to get into the decision rules, right? So we have all this data and we're going to say something like, "Oh, son, look at Gravedigger. He jumps 4 feet higher than everybody else does on average. You were right after all." So we need to decide about decision rules. We'll do some tests. We'll do a t-test, maybe a z-test, maybe chi-square. We'll look at p-values. We'll look at the importance of multiple tests. And then we'll go ahead and say, let's suppose we have this big sample and let's suppose we have this big population and we grab different samples out of that population. Well, we can form some tests between and among those samples, whether it's the sample mean or the sample standard deviation. Then we'll look at some parametric and non-parametric tests. And what I always love talking about are correlation coefficients. And then we'll finish with a test of independence on a contingency table that you guys will love when we get to the end. All right, so let's go ahead and start with that first LOS. Define an hypothesis, an assumptive statement about a problem or idea or some other characteristic of a population. So that's what I was talking about earlier, whether it's monster trucks or dividends or free cash flow. And look at that first blue teardrop point. An opinion, like my son had the opinion or a claim or a belief. And we might say something like, boy, as good fixed income analysts, we just know that bonds that have durations between 8 and 9, let's say, I'll pick that just as a range, bonds that have durations between 8 and 9 and have convexities greater than 200, these are the kinds of bonds that we want to own when interest rates go up. Wow, so we have this belief, so we need to collect all this data, and we need to base our collection and then our testing on solid fundamental analysis and solid fundamental statistical analysis, so that when we make a conclusion, we have confidence in it. Here's another example. The mean return of small cap stocks is higher than that of a large cap stock. So that's an opinion or a belief or a claim. How about the orange teardrop point? Collection and examination of a representative sample. Oh, you remember in that previous recording, we talked about all those different ways to sample. Now you understand, or at least during this slide deck, you'll even increase your understanding of how important it is to collect a sample that is representative, right? We don't want to collect, we don't want to have a population that has all these different data points and then only collect the sample down here in the bottom left or the top right. We want a representative sample. Second part of this LOS, describe the steps. And I've described these, kind of loosely so far, but let's do it in a more formal setting. So state the hypothesis, right? Gravedigger is the best monster truck driver out there. Select the appropriate test statistic. Now, if we can say that monster truck heights and lengths and noise, if they follow a normal distribution, then maybe we can use a Z statistic or a T statistic. We need to specify the level of significance. Like for example, if I say something like, you know what, I think that it's going to rain today. And my wife looks at me and says, well, how much confidence do you have in that? And I say 0%. She's going to say, what in the heck are you talking about, Jimmy? So we have to specify the level of a significance. And typically what the reading suggests, 90% sometimes, 95%, that sounds like a really commonly used level of significance, but sometimes we need even higher significance, 99% or maybe even 99.5%. So you, as a good researcher, you have to decide how confident do you want to be? Do you want to be 95% confident, which is a fairly standard level of confidence? Or do you want to be 99% confidence? Or like me with the weather, 0% confidence? My wife just ignores me, as well she should if I have 0% confidence. State the decision rule regarding the hypothesis. So at least it's either going to rain or it's not going to rain, right? And that's how we're going to make that decision. We calculate a sample statistic, and we'll do that throughout this slide deck. Although, if you remember going through those LOSs, there weren't too many go ahead and calculate, but there were lots of describe and understand. So we'll go ahead and calculate them for you so that you can do this. And then we'll go ahead and make the decision. And of course, the decision is based on the decision rule back in step number 4. All right, so let's go ahead and talk specifically about the formal hypothesis testing in terms of arranging this in a test that we can actually execute, right? What did my son say? Gravedigger's the greatest monster truck driver out there. Well, that's a little bit too general. We need to have something that is more specific. And so what we do is we form what's called the null hypothesis. And this probably represents, maybe a current state of knowledge about a population. Let's go back to my example with the fixed income analyst, and we're looking at all these different types of bonds. And so we know we have bonds that have low durations and mid durations and high durations. And so maybe the population duration is 10, but we think, or maybe we have evidence, or maybe we have a belief or a claim that maybe that population parameter should be 8 or 12 or some other number. So this is how we do this. We say the null hypothesis, which uses the notation H sub O. And what we're doing is we're just going to say mu is equal to mu sub 0. And that's all we're saying, that the null tells us that what we think is going to happen ought to happen. Now, if there's an equal sign in between that, that probably leads us to what's going to be known as a two-tailed test. I'll show you that here in just a second. But look on the right-hand side over there. We can have null hypotheses that have a less than or equal sign to, or a greater than or equal sign to. Let me just give you a quick example. Let's suppose that you collect lots of data on stock returns and you collect data on, let's say, the S&P 500 index returns, and you calculate the measure of systematic risk. And that's, of course, the beta. And so you might want to say that, oh, I think the beta is less than 1. That would mean less than average systematic risk. Or the beta is greater than 1. That means that this sample would have more than average systematic risk. And then the alternative hypothesis is just the opposite of what the null hypothesis is, and that's denoted as H1. And so what you do is if you reject the null hypothesis, then you go ahead and accept the alternative then must be true. That should make perfect sense. How about this LOS, one-tailed or two-tailed? I gave you just a little bit of a hint here on the previous slide. Notice that we have 3 normal distributions there illustrated. And we can have a one-tailed test where we're looking just in one direction. So look at the first one. We have a one-tailed test to the left. And so as we go through the CFA program, especially when we get to level 2, we'll talk about value at risk. At value at risk, we're always looking at the left-hand side of the tail. We can also look at the right-hand side of the tail. You know, what do we want there? We want to capture that right-hand side of the tail. When we do capital budgeting, I'll tell you a story that sounds something like this. You know, what do we want to do as executives? We want to invest in projects that have positive net present values, and we want some relatively high standard deviation in there so we can capture the right-hand side of those high operating cash flows. So one-tailed tests, we're just looking in one tail of the distribution. A two-tailed test, we're chopping it in half. We're saying that, okay, we know there's an event, but we're not quite sure that the alternative goes in one direction. We're interested in going this way or that way. That's a two-tailed test. We'll tell you more about those as the slide deck moves along. All right, let's go ahead and define a test statistic. Let me read that to you. Quantity calculated based on a sample whose value is the basis for deciding whether or not to reject the null hypothesis. All right, so what we need to do is we need to say something like, all right, my son thinks Gravedigger's the best monster truck driver out there. So we collect, and let's just do one, the height of all of his jumps. All right, and so let's suppose that height is 30 feet. Well, we need to decide if that 30 feet is statistically different from everybody else's heights. Heights or height. Yeah. So look at the formula for the test statistic. So we take the sample statistic, which was, what did I say, 20 or 30 for Gravedigger, and we subtract out some hypothesized value. You know, maybe my son says, oh, every other monster truck driver can only get to 20 feet, but Gravedigger can go to 30 feet. And then notice what we're doing. The standard error of the sample statistic. So we're standardizing this. I've said this to you in previous recordings, and I'll say this in future recordings as well, that when you take the difference between two numbers in the numerator, whatever those two numbers are, what did I say? Feet, the height of Gravedigger and all the monster trucks. When you subtract those two, you could get almost any value. And so what statisticians love doing is they love to squeeze that down. And so the convention is to standardize the test statistic by dividing by some type of measure of the degree of error. And in this case, it's the standard error of the sample statistic. Now, not in all cases, but in many cases, you just divide by a standard deviation. And so standard error is kind of a type of a standard deviation. All right, type 1 and type 2 errors, these are super important here. Type 1 error occurs when we reject a true null hypothesis. A type 2 error is the failure to reject a false null hypothesis. So I would just blink and memorize those two formulas if you haven't done that already during your lifetime. And of course, the level of significance, which is noted as the Greek letter alpha, represents the probability of making a type 1 error. power of the test, all we do is take 1 minus the probability of a type 2 error. And notice we have the muscles there, the power of the test. Do we want superpowers like Superman, or do we want just regular powers like Jim here? But this will determine the probability of correctly discrediting and rejecting the null hypothesis when, in fact, it is false. All right, so how about this decision rule? Let's set these up. Procedure followed by analysts to decide whether or not to reject the null hypothesis. So this makes sense. In order to do this, we need to determine whether or not it's a one or a two-tailed test. So let's go ahead and go through these. Case number one. A one-tailed test over to the left. So notice our alternative hypothesis is that the parameter, whatever it is, maybe it's the mean height of Gravedigger, maybe it's the mean dividend yield, maybe it's the mean convexity, is going to be less than some X value that we have decided as the researcher. So what we're going to do is we're going to calculate that test statistic like we did back here. Where am I? Right here. We'll calculate that test statistic, whatever that number turns out to be. And if it falls to the left, since this is a left one-tailed test, if it falls to the left of that critical value that we'll look up on the table, which we've done in previous recordings, by the way, then we go ahead and say that we want to reject the null hypothesis. We can do the same thing over to the right, a right one-tailed test. If the parameter is greater than some value x, and we do the same thing, but we're looking over on the right-hand side of that normal distribution. And so think about it right here. If we, let me go back to that previous slide. If we pick a 95% confidence, then all 5% of that alpha here, look at, what does it tell you on the illustration there? Critical region is alpha. So all 5% of that is thrown in the left tail. And then here for the right tail, all 5 of that is thrown into the right tail. But then if you have a two-tailed test, then you have to chop it. And we're chopping it in halves, so you have 2.5% on the left, 2.5% on the right. Look where it tells you here in this illustration, critical region, alpha divided by 2. And so make a note of this to yourself. Look at the alternative hypothesis there under case 3, H1. The parameter does not equal X. So what you're hypothesizing as a researcher is that the null hypothesis is that it does equal X, so the null is either above or below. That should make perfect sense. How about this part of an LOS? Determine whether a statistically significant result is also economically meaningful. I do have a slightly comical story about my dissertation defense. When you defend your dissertation, it's open to the public. And sadly, I must report that there was not an entire Super Bowl worth of fans at my dissertation defense. It was my committee and a handful of my fellow doctoral students who had not yet defended their dissertation, and they wanted to see how poorly I was going to perform. And one of them asked a question. They said, "Okay, Jim, I see that you have some statistical significance. And by the way, not that this is relevant at all, part of my dissertation was on the adoption of poison pill securities." And so one of my colleagues said, "You know, I can see that this has statistical significance, but does it have any practical significance?" So this is a great question. Is it economically meaningful? So we have to ask ourselves a couple of questions here. I'm going to go ahead and read that gray box to you. But before I do, I want you to think about this. You know, if we're doing things like measuring Gravedigger's greatness, and we're doing height and length and noise, maybe there are some other variables out there that are going to contribute to this, like wind. I don't really know if wind does it, but maybe does. Humidity, whether the track is wet or not, you know, making this stuff up. So look at that. I'm going to read this to you. When dealing with investments, some of the factors may affect the economic feasibility of that statistical result that we may or may not be interested in. So taxes and risk are the two that the reading emphasizes. All right, how about p-values? These are interesting. Lowest level of significance at which we can reject the null hypothesis. And so this is going to be super easy, as you'll see here in just a second. But let me go ahead and read that first pillbox point. It is the probability of coming up with a test statistic that would lead us to reject the null hypothesis, assuming the null hypothesis is indeed true. All right, so there's some arrow points down there, left one-tailed, right one-tailed, below and above, and then it's for two-tailed tests, it's the sum. So let's go ahead and take a look at an example. So this has some really good meaning to you. A survey carried out using a sample of 50 CFA charter holders. All right, so let's stop right there and ask ourselves the question, all right, a sample of 50. How many CFA charter holders are out there? Well, the last time I checked was sometime in 2021, and I think the number's around 170,000. So I want you to think about this. So the population is 170,000, and we're taking a sample of just 50. Oh boy, now you understand. This is a great example and a great application of the emphasis that I placed in those previous recordings about the importance of sampling. And so what are you tempted to think? You ought to be tempted to say, boy, how can a sample of 50 be representative of 170,000 in the population? And that's a good temptation. However, this is what we know. We know that if sampling is carried out properly, like those previous recordings showed us, then a sample of 50 might be, in fact, it might be a great indication of how the population, what the population really looks like. All right, reveals an average IQ of 105. Oh boy, I'm pretty sure that sample of 50 didn't include my IQ. Baba boom, how about that for a joke? Of course, my wife would say, yeah, Jim, you're way, way below that. My son, the Gravedigger fan, would say otherwise, though. Of course, I'm just kidding here. All right, so previous studies have shown that IQs are normally distributed. That makes sense. Standard deviation of approximately 20. All right, so here's the question. Using a 5% level of significance. So what does that mean? That means that we want to be 95% confident in our concluding remarks, right? That's very different from the 0% that I said just a few moments ago about how confident I was that it was going to rain today. Is the mean IQ of CFA charter holders greater than 100? All right, so let's take a deep breath and just ask ourselves this question like we were in kindergarten, right? So a kindergartner would say, wait a minute, 100, right? 100, that's less than 105. Of course. Is the mean IQ greater than 100? Well, of course it's greater than 100. It's 105. We just showed you that the mean is 105. But the 100 and the 105 have not been statistically evaluated. So even though 105 is greater than 100, it may turn out that the answer is no. And it all depends on things like what we do in the denominator. All right, so let's go ahead and put together this test. So there's our hypotheses. So the null hypotheses is that the mean is 100. And the alternative is that the mean is greater than 100. And so what we're doing is, since those IQs do follow a normal distribution, which I think we've known for a really, really long time, then what we can do is we can compute the test statistic. All right, so look at the very bottom there. We're going to take 105 minus 100. So there's the 5. We learned that in kindergarten, but we have to standardize it. We have to divide it, and we're going to divide by the standard deviation of 20, and then we need to divide that thing by the square root of n. N was our 50 CFA charter holders inside of that sample. So our test statistic is a 1.768. What we do is get out our z table. Let me just remind you that if we have normal distributions, then and our sample is greater than 30, then we use the z table. If our sample is less than 30, then we need to use the t-distribution. Remember, those kind of converge to each other at high sample sizes. So all we're going to do is run our finger down till we get to 1.7, right? So let me just go back here real quick. 1.76. Now these tables are just two-dimensional, so we can only go to two decimal places. So you have to round. So 1.768, we'll round that up to 1.77. Run our finger down to 1.7, and then run our finger across to 0.07. So the column 1.7 plus the row 0.07, that gets us a sum of 1.77. And so there's our z at 9616. Subtract that from 1, and we get 3.84%. And let's go back here. What did we say? Using a 5% level of significance. Well, there we go. 3.84 is less than 5%. So we have sufficient evidence to reject the null hypothesis at the 5%. So what do we say? Let's go back here. What was our null? Our null was that the mean is 100. So we say, we learned that in kindergarten. And in fact, based on all of our data collection, the kindergartners were right. But the kindergartners don't have to be right all the time. And that's why we divide by that weighted standard deviation by the sample size, right? 20 divided by the square root of 50. We want to be sure. We want to prove it, because we're at a much higher level than we were back in kindergarten. So look at that LOS up there. Explain and interpret the p-value as it relates to hypothesis testing. So I can envision a question under which the institute gives you a bunch of stuff like this, right? There's the question stem, gives you the resulting t statistic, and then maybe gives you that 9616 from the table and says, what kind of a conclusion can you make? And you say, oh yeah, we reject the null hypothesis. Now, that previous example was really good because I want you to think about this. So we have 170,000 individuals who hold the CFA designation. We took a sample of 50. So what are we tempted to think? We're tempted to say, you know what, we're great samplers. We did all that stuff that we were supposed to do in those previous readings about collecting a representative sample. So therefore, we can put all of our eggs into the one basket and say, yes, we're rejecting that null hypothesis. But we might want to scratch our head and say, let's take some other samples. We did 50 here, let's do 50 here, and let's do 70 here, let's do 100 here. Let's do multiple testing. Well, this brings us into this concept of the multiple testing problem. So look at the example in the second bullet point there. If 60 tests are run, we will have 3 false positives using a 5% level of significance. This is called the issue of multiple testing problem. And that's because this sample and all these multiple samples, they're going to be different samples. And so we may have some kind of a false positive. So we need to try to figure out how we can test if we have a significant false discovery rate. So this is what we're going to do, this false discovery approach. Here's the process. We're going to rank them. We're going to compare using that formula right there. So notice there's the alpha in there. So there's the 5%. And then we're going to rank and divide by the number of tests. So there we're standardizing just a little bit. And then we're going to compare. So let me go ahead and show you a quick example. Suppose our hypothesis is that a population mean is equal to 25%. The sampling process is repeated 30 times and 30 sample statistics are calculated. Out of that 30, the table below reflects the lowest 5 p-values. Okay, so lowest 5 for 5 statistics, all right? And there's 5%. Notice that we put that in red. So going down the left-hand column, which of those p-values are less than the 5%? Well, notice there's a 3 and a 15 and a 27 and an 8 and a 0.01. So only the 0.3 and the 0.1, those would be significant using just the p-values. And remember, these p-values tests are crafted and hypothesized based on the simple fact that you're only taking and performing one test. But here we're doing multiple tests. So look at that first diamond point. Based only on p-values, we would have only two tests in which the null hypothesis will be rejected. But if we do this process back here, this false discovery approach, and there's the formula right there. I want you to look at that pretty quickly. We're going to perform this next kind of a test, Benjamin and Huckberg. Just remember it is HB. And so this is what we're going to do. We're going to rank them. So the 001, that's the number 1, and the 0.27, that's number 5. So you see how we just ranked them there. And then we're going to use that formula from the previous slide, and all we're going to do is multiply that 5%, our level of significance, times the ratio of each of those rankings out of the total 30, right? It's still out of 30. And then we get a number there, right? So that's the BH criteria, and then all we're going to do is compare that number to the value over in P. And so is it less than or equal to the value in column 3, right? The p-value versus column 3. So we have no, 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 and then yes. So there's only one significant test. And so why do we do this? And this is really fascinating. The reading really emphasized this, and I think this is the great exam question. This is true when a couple of things occur during your test. Suppose that you perform this test and you get no significance. Well, then maybe we need to go ahead and do a couple more of these tests. We need to concern ourselves with kind of data mining, right? We don't want to pick and choose. But this problems with multiple testing is going to occur when the sample size is relatively low. And that's probably the great exam question that you should answer. All right, moving on to this idea of continuing to test large and small samples, comparing the sample to the mean, and then in a little bit we're going to compare two different samples. So here we have the normal distribution picture there on the right hand side. And so look, we have scenario 1. So we're assuming normal distribution. We're going to use the z statistic, and there it is. We've already done that in the previous slide. Okay, what we're going to do is compare that z to the critical value from the table, and then make an accept or reject decision depending on whether that z falls in that critical region. So here's the key part of this formula. Notice that we have z, there's the numerator, right? Two means, subtract two means, and we're dividing by, there's a sigma in there. So look at scenario 1, right? When the variance of the population is known, then you use this formula. That's super important. Of course, your next question ought to be, well, what if the variance is not known? Oh, well, here's scenario 2. When the variance is unknown, then what we simply do, notice this is the exact same formula there, but instead of the Greek sigma in the denominator, we have the sample in the denominator there. So here is the population variance when it's known. When we don't know the population variance, we're just going to substitute the sample variance, or in this case, the sample standard deviation. Now this, back here, this is a z. Here, this is a t distribution. So that's super important. So make sure you understand the difference between scenario 1 and scenario 2. Two differences. Here we have z and the population standard deviation. Here we have t and the sample standard deviation. So as you're reading the question stem, you know you could have hundreds of questions like this on the exam. Of course, you're not going to have hundreds, but you could have 2 or 3. One, they'll give you the variance. One, they won't give you the variance. Now, going back to the CFA example, we have 170,000. Let's suppose we pull out our original sample of 50, and then we pull out another sample of 50, right? So we have these two samples. What's the next logical question? The next logical question is to say, hey, are those two samples the same sample? Now, they're not going to be the same, but are they the same statistically? So look at that first orange arrow point. We might want to establish whether there exists a difference between the means of two different populations. Now, in my case, I said two different samples, but maybe you have two different populations up there. All right, so scenario one, difference between two population means, small samples with a common pooled variance. All right, so two independent random samples of size N1 and N2 with means of X1 bar and X2 bar and variance there. This is what we're going to do. So what's our null hypothesis? Our null hypothesis is that the two means are equal, but a lot of times statisticians like writing it in the following form. Mean 1 minus mean 2 is equal to 0. So look at our illustration right there. We're just testing to see if those means are the same. How do we do this? We use our t-statistic. And since we have two samples, we have to have n minus 1 degrees of freedom here and n minus 1 degrees of freedom here with the two samples. So it's n1 and n2. So we say n1 plus n2 minus 1, so there's the minus 2 degrees of freedom. So all we're doing in the numerator is taking the difference between the two means. We do this all the time, right? So this should become super familiar. And then we're going to divide by some kind of measure of volatility or standard deviation or an error term. And so we're going to divide by the pooled standard deviation. And there's the formula for that in blue. And notice we're just taking the variance of sample 1 and the variance of sample 2. And we're kind of weighting them, right, by n minus 1 and n minus 1 degrees of freedom, and then dividing by all those degrees of freedom. So they kind of almost cancel each other out. And so that gives you the denominator there, the pooled standard deviation. And then you have to, of course, take the square root of 1 over n squared, just like we did before. How about the difference between two population means with large samples? Back here, we have this problem of, what did I say, 50 and 50. Now, that 50 and 50 would probably fall under the Z. But if we back here had 5 and 5, then we'd probably use that t-statistic. But here, notice that we're doing, this is the exact same formula, but we don't have to pool. We don't have to pool those individual samples because those samples are large. How about this concept here? Sometimes the difference between the means of these two populations can be the result of the relationship that we think of, but it might be the result of another relationship that we're probably not too interested in. And this is what I was saying earlier about Gravedigger and the wind and the track wetness and, what did I say, humidity or the barometer, whatever that is. And so what we do in order to solve this problem of, notice we have in parentheses or in bold, masked by variability within each sample, we can do a paired data test. Let's take a look at an example. Suppose there's any difference between pre-dividend and post-dividend share price within an industry. So we collect stock price samples 7 days before, 7 days after, and what we're going to do is we're going to pair the data and then we can perform a test. So this is what we're going to do here. So there's the null hypothesis that the mean difference, or mu1 minus mu2 is equal to 0. And there's our t-statistic. And so once again, we're just subtracting means in the numerator, and we're dividing by some measure of a degree of error. And there are some good formulas there. D bar, we're just taking the average of all the D's, and then the standard deviation, we're calculating standard deviation just like we always have. All right, so what have we done in those last handful of slides? We've looked at means, right? The difference between the means, but suppose we want to figure out about standard deviation or the variance. So maybe we want to ask our question, is that sample standard deviation in our 50 sample size for CFA charter holders, is that the same thing as the population standard deviation? So there's our null hypothesis, that the sample standard deviation, or in this case variance, right, because it's squared, is equal to the population. Now, when the underlying data follows a normal distribution, which we think it does, right, then when we test the variance, then it's appropriate to use the chi-square test. We did the chi-square test in a previous reading. Let me just remind you, chi-square tests are truncated at 0, so they can't ever be negative. And so those chi-square distribution, that illustration, is going to be skewed. And there's a picture of it. And if we're doing a two-tailed test, we're going to chop that alpha into both tails. Notice the two tails are not equally distributed like they are in a normal T or Z test with a normal distribution. Let's go ahead and work through an example here. 15-year period, stock's monthly return has a standard deviation of 5%. So this financial analyst wants to know if this adequately describes the long-term standard deviation. This analyst collects monthly returns for some time period and monthly standard deviation of 4%. Carry out a 5% test to determine if the standard deviation computed in the latter period is different from that 15-year value. So this makes perfect sense, right? And once we hit level 2 and maybe even sometime in level 3, and we talk about the Black-Scholes-Merton option pricing model, the most important critical variable as an input in Black-Scholes-Merton is the standard deviation of the underlying asset. And so we want to know if the current standard deviation is representative or not. Boy, if we knew, and this will make perfect sense to you as we get through the program, if we knew what the standard deviation of a share of stock was, boy, we could make a ton of money in the options market. But that's a conversation for a different day. So here we're asking ourselves the question. Notice we have it in red, standard deviation of 4. Notice we have it in blue, standard deviation of 5. Are those the same numbers? Now, back in kindergarten, we would clearly say, no, they're not the same numbers, but we need to support this with a chi-square distribution. All right, so there is the hypothesis, and notice that's in variance terms, so it's equal to 0.025. And the alternative is a two-tailed test, right? So it's not equal to 0.005. So just plug in all those numbers in there, and you get a chi-square of 14. And remember that the chi-square distribution is defined by just one set of degrees of freedom. So all we have to do is go down the left-hand column. So we hit 23, right? What did we do? We collected 24 months, so n minus 1 is 23. So at the 5%, so we chop that in half, right? 2.5% on this end and 2.5% on that end. But now, since this distribution is truncated at 0, we need to be a little bit careful here. We're not going to find 2.5 on either side. We'll find 2.5 on the right. So that's, what is that number? 38 something. And then 1 minus 2.5, that gets us the 97.5. So what is that number? 11 or 12. And so our 14 fell in between 11 and 38, right? So we have insufficient evidence to reject the null hypothesis. So here's an example of where the kindergartners were wrong. Our earlier example, the kindergartners were right. Here, the kindergartners were wrong when they said, wait, 4% doesn't equal 5%. But now that we prove this statistically, we say that there really is no difference between a 4 and a 5% standard deviation. Now, let's go back to my example where we took out 50 and then we took out another 50 and we tested the means of those two samples for our CFA charter holders. Now we want to say, well, what about the variance? What about the standard deviation? So our null hypothesis is that the two sample standard deviations, or in this case variances, since they're squared, are equal, and the null is that they are not equal. Well, when you're testing, you should remember this from a previous reading, when you're testing the difference between two standard deviations or two variances, you need the F distribution. And the F distribution is very similar to the chi distribution. However, since there are two samples, we are defining the F distribution by two sets of degrees of freedom. So you need a degrees of freedom in the numerator, right, for sample 1, and a degrees of freedom in the denominator, right, for sample 2. All right, how about this LOS for comparing and contrasting parametric and non-parametric tests? All right, parametric tests, this is what we've been doing. Statistical tests in which we make assumptions regarding the distribution of a population. So we've done all this before. We use that Z statistic or the T statistic. Non-parametric tests, on the other hand, these are called distribution-free tests, are tests that do not make any assumption regarding the distribution. All right, so here we go. When do we use this thing? And this is probably the really good exam question. I like the second one. Sample size is pretty small, less than 10. If we have to rank these things, if the data is ordinal and they have a natural ordered kind of a sequence, or when the hypothesis being tested does not concern a parameter, what have we done? We've used the parameters, right? The mean and the variance so far. But maybe we want to do something else. Here, I'd said this in the very beginning that I love talking about correlation coefficients. So of course, we can test that a population correlation coefficient equals 0. And there's a good formula for the test statistic. Even though the LOS doesn't ask you to memorize this and use it for the exam, you probably have to do it at some other point during your CFA studying and testing. One key thing about this, notice that in the numerator, we have the R, the lowercase r, that's the correlation coefficient there, times the square root of n minus 2. So there are 2 degrees of freedom because if we're, correlation measures the strength and the direction of a relationship between two variables. So if we have this variable, it correlates with this variable, and we have this variable correlates with that variable. So there's 2 of them in there. And so our decision rule at the bottom is exactly the same as it has been before. And correlation coefficients are normally t-tests. Sometimes we want to determine the strength and the direction of a relationship between two variables that may or may not involve things like the mean and standard deviation. So notice this Spearman rank correlation coefficient. Notice what we have in bold: significant relationship between two sets of data. So what we're asking ourselves here is the following. Let's suppose that we're determining the correlation coefficient between, stock returns of an individual stock and market returns of the S&P 500 index. And we can put these in an Excel spreadsheet, and we can very easily calculate the correlation coefficient. And suppose that correlation coefficient turns out to be, 0.1. And so we can go back to this test right here, right? We can say our null hypothesis is that the correlation coefficient equals 0. And, we can do all that stuff and we can make a conclusion. But maybe we're wrong. Maybe there's something else to the story. And that story involves this non-parametric test of the Spearman rank correlation. So there it is, R sub S. So that S is for Spearman, and the R is the correlation coefficient. And there is this massive formula in there. And so I'm going to go ahead and skip over that for just a second. I'll come back to it, but I'll skip over it just a second. And what I want to do is I want to waste a few more minutes of your time by going through these steps. So we're going to rank the values. We're going to find the difference. We're going to square the difference and then sum those differences and then calculate the Spearman rank correlation coefficient. And so I wasted your time because those probably didn't make any sense at all to you. And that's, of course, why we have an example. So you ready for this? This will make it perfectly clear. So let's go ahead and do the Spearman's rank correlation and the test statistic. All right, so here we've got 5 years of data for stock returns for steel industry and the cement industry. So down the left-hand column, years 1, 2, 3, 4, and 5. So there are the steel industry or steel sector returns, cement sector returns. Now we could calculate that correlation coefficient between those two returns, but watch what Spearman does in excess of what the regular old correlation. All right, you ready? So what we're going to do is put this in a big old table. So we're going to rank X and Y. So let's just go down X. What's the highest return? 5.6%. So we give that a 1. What's the lowest? A -3. So we give that a 5. So you see the column rank of X, 1, 2, 3, 4, 5, in order from 5.6 all the way down to a -3. And we do the same thing for the rank of Y. There was 4.5% for Y. That was the highest return, and -1.7 was the lowest return for Y. So we have those ranks and ranks. And here's the cool thing about the Spearman's test is that we turned some parametric stuff into a non-parametric ranking. But sometimes you don't have, here, let me go back here. Sometimes you don't have those returns. All you have are the rankings. And so if you calculate the regular old correlation coefficient with those rankings, then your answer is going to be way, way off. And the conclusions are probably going to be incorrect. All right, so we have those ranks, then we calculate the D. Here, let me go back to the steps. What was the first one? All right, so rank, we did that. So now you see how interesting that is and how easy that is. Find the difference. All right, so let's find the difference. So 3 minus 4 is a -1. 2 minus 1 is 1. 1 minus 2. All right, so you get the sense there. So there's our D. And let's square it. We're squaring it over there to get rid of the negative, right? And so we sum that and we get 4. So now we are ready to go ahead and throw that back into the equation. And so notice down in the left-hand box, we have the Spearman's correlation. It's 1 minus, and there's the number 6 times the summation. So that's the 4. And by the way, that 6 really exists to remove the reliance on the number of observations, 5 here, and also to link it to the ranking, the 1, 2, 3, 4, 5. I wouldn't worry about that at all. Just remember that it's 6. And you get 0.8, right? So there's our Spearman's rank correlation coefficient. And we can compute the t-stat using our regular old formula, and you get 2.309. So there's our t-stat, 2.309. Now, the reading is very interesting, and I'm always fascinated by this stuff in terms of how the CFA approaches this from a test-taking standpoint. There's a sentence in there that says, for small sample size, you need a special Spearman's table to find the critical value, which there's really no evidence and there's no documentation inside of the reading. So I wouldn't worry about that too much. What I would say is that, look at this, explain and determine whether the hypothesis is rejected. So I would be able to just assume that this is for a large sample, even though this is not in this particular example, that t of 2.309 is for a large sample, and you can just go look up the t-value like you do in any other table. Now, how about let's form this contingency table, and this is based on frequencies. And it's based on frequencies that are going to have a chi-square distributed test statistic. And so look at this chi-square. It's going to be observed frequencies minus expected frequencies. So it's just really just in the numerator, it's just once again differences between two things. Maybe it's a mean, maybe it's something else, but it's probably a mean. We square it and then we divide by the expected frequency. And notice M is the number of tables because we're going to have a table here in just a second. And so once again, that formula doesn't mean anything to you until you look at our example. All right, so you ready for this? 2 categories of investors. One category is employed, one category is retired. Total sample size is 133. So look at the primary investment objectives in the table. We have categories, growth and income, and both. For the employed and for the retired. And this is a great financial analyst question. If I have clients that are working, if I have clients that are retired, do they have different objectives? So this is a great question, and we can use this contingency table to help us answer that question. All right, so after a survey, you got 84, 72, and 17. So notice that those sum to 173, both in the rows and the columns. Now that we've looked at this table that describes our clients, let me quickly go back to this chi-square formula, and I want you to close your eyes and I want you to take a picture of that, a mental picture of it. Even though it still doesn't have any meaning to you, let's go ahead and see how this formulates itself on a table. But first, let's go ahead and put together the null and the alternative hypothesis. So null hypothesis, no significant difference between employed and retired investors, and then the alternative hypothesis that there is a significant difference between those two groups. So that's what we're going to do. Look at number one, calculate the expected frequency using that formula. So ready, close your eyes and draw that formula from your brain. And here's what we're going to do. So we have that table up at the top. There's the observed frequency, and let's go down and compute expected frequency. So notice what we're going to do here. We're going to take 87, which is all the way over for the employed total. We're going to multiply that by the growth total, 87 times 84, divide that by the total. So there's the expected frequency of 42.24. And we do that, we multiply the totals, right? So let me go back here. So there's total of row I and total of column J. Let's go way back here. So there is the observed frequency minus the expected frequency. All right, so we're getting there. And we do that for growth and employed, growth and retired, income and employed, income and retired, and then both employed and both retired. All right, so notice that we've got a whole bunch of extra data points in here based on observed frequencies and then kind of average frequencies or expected frequencies. So all we're going to do is use that equation from before, 52 minus the 42, square that, divided by the 42, and we get all those kind of what I think of them as, kind of mini chi-square numbers, and then we sum the columns, and then we sum the row, and we get 12. Critical value is 5.99. Now remember, when we do this frequency thing, since we have two separate groups, we need to do rows and columns to determine our degrees of frequency. So it's going to be R minus 1 and C minus 1. So we have two degrees of frequency. 2 degrees of freedom. So you look that number up in the table, you get 5.99, and 12 is way past this. So we're going to reject the null hypothesis. So what was our null hypothesis? That there is no significant difference between the employed and the retired. What do we accept then? We accept the alternative hypothesis saying that there is a significant difference. This is a really cool outcome here that occurs at the very end. Notice that we had 3 slides of learning outcome statements. I can't really decide which among those is super important, but my advice is to start at 1 and keep going and work your way till you get to the end. Each of those is important, and each of those have the potential for great exam questions.